So next, let's look at page 252, where we look at subsection 6.5, the vector considerations. This subsection is actually just the author's quick, well, I guess it's not that quick. It goes this whole page, and most of the, it goes almost 3 pages, okay, 2.5 pages of this stuff. That's talking about how Green's theorem and Stokes' theorem work in physics, if you consider things as vectors. For example, the divergence theorem, look at this thing right down here, okay? This thing doesn't look very familiar, but this is just Theorem 8 written in the vector form. So please read this yourself, okay, and confirm that this is true. To confirm it, you have to know that the theta is on page 106. That's the normal to the surface sigma. And Theorem 8 on page 235 is just this, okay? And then the divergence is defined on page 80. Once you get all those pages and flip through all of them and look back and forth, you realize that this is indeed just a restatement of Theorem 8. And then so please read this part yourself, as well as the next page, in fact the whole section, because there's not much happening that the author is trying to talk about what divergence might mean in physics, which was already talked about in basic calculus back when we first learned about Green's theorem and Stokes' theorem in Calculus 3. So I'm not going to repeat it here. And there are a couple of simple examples that I think you can readily figure out what it's talking about if you just read it carefully. So please read through all this stuff, okay? And also the Stokes theorem has something to do with a curl. And if you look at the definition of curl on page 80, then you will see why this is the case. This is just a restatement of Stokes theorem, Theorem 10, right here. So it's the same thing. And then and anyway, so all these things are just, well, basically comments that I'm not going to repeat it. And not all of it is mentioned back in the day, but none of these are really very exciting to tell the truth. And then, so let's turn to page 254, where it mentions something about some equation. I will show you what I wrote down. On about page 254, okay, where well, there's this simple, there's a simple integration that the author mentions. I don't even know why. I mean, look at this thing. I'm not sure it's worth mentioning, but I wrote it down, and so please read that yourself. Because yeah, and so on. And then of course if curl y is C equal to 0, the field is called conservative. You might remember that from Calculus 3. And then the big F that we've been working on has a name, and it's called the potential function, which that doesn't really concern us. We just want to know the math, and then what it happens in physics is let the physics people worry about that. So with that we have. So please read all this stuff yourself, okay, carefully. And just because the author wrote it and we paid for the book, we might as well get every last inch out of it. But once you're done, it's yeah. But don't expect too much math out of the deal. And we have come then to the end of this section, which is a rather long section with more pages than usual, which is okay. All right. And so let's do homework. This is so for homework. Let me first write it down. Okay, so for homework, please do, which is on page 254, please do problems 1, 2, 3, 4, and then 10, 11, 12, 13, 14, 15, 16, 17, and 18. And when you're done, I want to talk about them. Let's start with problem 1, where we're supposed to do the example A on page 247 for the curve x equal to cosine t, etc. Okay, so I have it right here. Where is, I think, yeah, better be. Okay, so here's problem 1, where we plug in all that stuff, okay, and then out pops the answer. Where's the answer? Oh, 0. That's where it is. It's clear on the other side. So the answer is 0, and that's that. I also want to show you what I wrote on the calculator what the calculator wrote. Okay, here it is. That's how I typed it in, and out pops the answer 0. That turns out to be correct, so I'm good. So that's problem 1. Next, problem 2, which we are supposed to calculate this thing, which is fine, and then we have to do it the hard way by using Stokes' theorem and expressing it over some surface integral, blah blah blah. Okay, what's the surface integral? It doesn't matter what surface integral it is. Let's see, indicate which normal, whatever. And that's we're doing problem 2. All right, so problem 2, first we'll do it the old-fashioned, the direct way. Okay, I have written right here. And the answer turns out to be clear on the other side is -4 pi, which checks out with the answer at the back of the book. And here is, and I used the calculator, and you notice that the answer is also for problem 2. Okay, the answer is -4 pi. And yes, and it did it all without me having to, move a brain muscle, because I sure don't want to bother with that. All right, so that is problem 2, and the first part, the easy part. The second part, we have to use Stokes' theorem, which means we have to go through a bunch of busy work. Okay, we have to figure out where the normal is, and that's roughly where that got, and what is sigma, and then the normal to sigma. Okay, that's that information. And then and we're going to integrate it in the projected region, which is R, which is right here. And then we plug it into the Stokes theorem. And luckily, there are a bunch of zeros, so make things somewhat easier. And by the time we got all of that done and converted into polar coordinates or something, it did give me -4 pi, which is what we figured out before. So that is problem 2. So next, let's consider problem 3. We're calculating this thing. We have to do it in 2 ways. First, by a broken line. Okay, we have to integrate some line that is going vertical or horizontal. Okay, broken line with segments parallel to the axis. They won't even let us pick our own broken line. It has to do the parallel to the axis trick, and then we'll find it directly. All right. So to do that, we have, what is this? Problem 3? Yeah. Here it is. Right. So problem 3, I have, let me see. Okay. First, we have to, first I figured out what the direct way is. Okay. That is, I found the big F. The big F, then we just do the subtraction. Once we figure out what the big F is, then we just do the subtraction, and we're home free. And then the second way, I did the broken line trick. And the broken line I picked, you can pick any old broken line, right? So, but anyway, the line I picked just goes, I think this directly, this is vertical, maybe? No, this is along the y-axis. Okay, y-axis changes from 0 to 2. And then z-axis changes from -1 to 3. So path A is, I have 2t changing. And path B, I have this thing changing, okay, both going from 0 to 1. And then I integrate both things, and then the same answer came out, is 6. So that is problem 3. So next, problem 4. We have this integral, and we need to calculate, the integration. Now to calculate that, we are going to use the handy theorem, of course, which is on page 251. Where we're just going to calculate this thing with by finding the potential function, or the big F, okay, and by applying theorem 12. However, to apply theorem 12, we have to show that this condition 2 actually does apply and verify all that. And that is what I did on the calculator, of course. I wasn't going to do this by hand. I mean, it's like, and okay, now can you see that okay? It looks okay, I guess. And so as you can see, I have shown, I did Q3, and then show that it equals to R2, R1 is equal to P3, and P2 equal to Q1. Now this might look like a lot of typing, but it really isn't bad because everything looks is pretty similar. I just copy and pasted and changed a couple of things, okay, and to be able to do all to get all this stuff out. And then the integration, the big F, at first I didn't know how I was about to integrate that. That looks complicated. But as it turns out, it's just sign of that thing. Okay, all that wasn't as hard as it looks. So then I was able to find out what big F is. Once big F is found, then we are good to go. And so we plug it in. What did I say big F was? I thought it said something about sign. Let me see. So yeah, it is, the big F is sign of this thing. So then we just the integral is simply the f of value on top minus f of value on bottom, which end up after some work, then you realize it's just 1, and that is problem 4. And next problem 10. Problem 10 is about this. Is proving theorem 11 backwards. That is, theorem 11 proves forward in the sense that this stuff proves this is the case. Now we have big F. We need to prove that is true. Now that's much easier because that's just a matter of mixed partials being the same. Okay, so I have it written out here. As you notice that Q3 is F23, which is F32, which is R2, and so on. So then so problem 10 is a really quick problem. That is that. So next, let's look at problem 11, which states that we have these. Problem 11 shows that the surface integral is independent and so on if P1 plus Q2 plus R3 equal to 0. In other words, we have to make this thing fit Stokes theorem. Okay, and then because that's what, or theorem 11 or something, that's what makes everything come out. Is let's see, yeah, we have to make sure that this trick applies. So as long as this is true, then the integration is independent. So that would be theorem 12, I guess. So to make this thing come out, then we have to. The book actually gave us a hint, which is good, I guess. And so to use Stokes theorem, okay, we then have the first 3 things, and then it then equal to this, and these things it has to work out in such a way that this double integral over sigma has to work out such that P has to be equal to the C2 minus B3, and Q equals to what is that, A2 or A3? What does that say? 3. I think that's a 3. Anyway, it's the same thing that the book says. Okay, so the reason is because we need to have these things line up with each term such that everything works out to fit the Stokes theorem. And the book actually even gave us not just that we do these ABCs, but that C can be arbitrary, which means let's choose C equal to 0. Okay, if C can be anything, we'll pick it to be 0, which that makes it easy for us to figure out what Q is from this equation. Q is equal to A3 because being that C is 0. Then all the partial derivatives are also 0. So then we can calculate what A is. Okay, and so that got us A, and then similarly, we also got able to come up with P, which gave us what P, relationship between P and B, which gave us what B is. So we got A and B, and then over here, since A2 and B1 are calculated this way, then B1 minus A2, which equals to minus Q minus P, is equal to R3. Why is that? Because we're given that P1 plus Q2 plus R3 equal to 0. So that means that is a given in the problem, which means minus Q2 minus P1 is equal to R3, and the integrating over dz would be just R. Okay, so with all this stuff, then we're able to show that this thing is equal to and this integral, okay, is equal to the AB and stuff. And that is by following Stokes' theorem that I have written on top, okay, where ABC is written in gray, so it's harder to read, but that is the idea. So then, and being that C is 0, so we just have this, and in any case, it does not depend on sigma. And that's how problem 11 is done. Well, just like what the book says. So next, let's consider problem 12. Well, problem 11 is when that was the end of my Disney trip after a week. Okay, I did all that until when I first mentioned Disney, whenever that was. And then problem 11 was the last one. And problem 12, I did it at the airport. See, it says right here, end of Disney. I did problem 12 at MCO. So problem 12 is, we're going to do this as, now first let me figure out what it says. Problem 12 says that we're going to calculate this thing over any surface, which means we're not going to do any surface. We're just going to calculate it, find the boundary, and crank it out that way. Okay, so then that is problem 12. All right. Anyway, so problem 12, we have, what we're going to do is, right, we're going to assign the fit it to the Stokes theorem. Okay, so here's problem 12, and I have Stokes theorem written down in the previous problem. So we're going to fit, what was it? Yeah, the R2 minus Q3 is going to fit into the P position equal to X, which is in the P position. And then P3 minus R1 will be the Q, whatever's in the Q position, and so on. And then we are going to do things that way. So we'll choose P2 equal to 0. Why is that? I guess one of them we can just make it 0. They don't all have to be something. Okay, if we choose P2 is 0, then Q is equal to this thing, and that's Q1, which we can calculate what Q is, which is over here. Okay, and then next, so we're already choosing P2 equal to 0. Let's see. Anyway, so Q3 is this thing, which means we're able to, R2 is that, which we can calculate R, and then P is 0, because we're choosing P to be 0. So then the integral according to Stokes theorem on top, then will be equal to that pile of stuff, okay? And everything works out, which equals to this, and then it end up being 0, which is okay. And I did all that at the airport. And after that, I stopped. Well, I still had time, but I was super tired, and yeah, extremely tired. So I couldn't do any more. But I was able to do problem 12 at the airport, and I also typed it out into the computer, and that's the answer. I don't know if you need to see that, but there it is. Okay, here's my book. Anyway, so we have next, we do problem 13. 13 says we're going to solve this thing by multiplying a suitable function to make it work. All right, so let's, because the thing by itself is not going to come out, okay? So because, let me see. Do we know that it doesn't come out? Let me check. Well, give me a second here. Yeah, that's because by itself, if we don't multiply by something, some helping factor, it's not going to work. For example, Q3 is not equal to R2 if you were to check it. Well, yeah, I scratched that out, but anyway, that part, I did that part in the airport too, but I was so confused. After a while, I just decided to stop. And so anyway, and so then I got home, and then my brain was much better. And then and I did this after I had plenty of rest. Okay, so let's multiply by f of z, and so then we have so that thing is P, and that's Q, and that's R, and we needed such that Q3 had better be equal to R2. Okay, so then that will give us some kind of equation, right? This is a differential equation, which end up being something like this when we beat it around a little bit. And how do you solve this differential equation? Please refer to Calculus 2, page 381. This thing has a name. It's called the separable differential equation. And it's, if you don't remember it, okay, take a quick look. You'll remember right away. It's pretty straightforward. You just, you just do do this, basically. And then integrate both sides, and then the answer pops right out. And after you assign C1 to be just 1, because we're just making this up anyway. So so our f of z, it becomes c to the power minus 2. That's a 2 up there. And anyway, so putting that back into our original equation, then we'll have something that everything will work out. Okay, that the Q's, Q3 is, what is that? Here's R2, and what? Why do I need all that? Let me look at it. Oh, anyway, the point is everything checked out. And in the sense that, then R2 is equal to Q3 by the time we do all the algebra, okay? And a differentiation algebra. And P2 end up being Q1, and P3 equals to R1, just like the Stokes theorem requires. So then everything is good. So let's look at the next page, and then our original equation, we changed it a little bit into the new equation, and after we with that we're able to integrate, and becomes big F is equal to xy over z equal to the constant, or xy equal to constant times z, which is the answer at the back of the book. So far so good, and that's problem 13. Next, let's look at problem 14, which says that, let me see, what does it say? Nothing. All right. So problem 14, let me see what it says. Problem 14, we're just going to solve some equation. Okay, so we're going to solve it the same way we just solved the previous one, by adding some kind of f of z in there to make things come out. Okay, and then do the differential equation just like in the previous problem. So that is how it's done. Okay, we figured out what Q3 is, and we did the differential equation, which come out f of c is equal to c to the power minus 1. And with that, we plugged it in, and then able to come out with a big F. And big F, after some cranking around, then we figured out big F is going to be, has to equal to natural log of z plus xy equals to constant, and that checks out with the back of the book as well. Okay, so that is that. Well, I see that I forgot to show you this for problem 13 and 14, the separable differential equation, how to do that on Calculus 2, page 381. I have a screenshot here where it says, to solve this equation, you do this, okay, and then integrate both sides, and everything will come out very nicely. And that's that. So next, let's look at problem 15. 15 says, apply Stokes theorem to show that, to 2/2 of the sphere, to show that this thing is going to be equal to 0 over the entire surface of any sphere. And that's because when we apply Stokes theorem, which states that the integral around the gamma is equal to the double integral over the surface, right? Now, if that's the case, then if you have two surfaces, and the gamma then goes, for the top surface, the gamma goes one direction, and for the bottom surface, the gamma goes the opposite direction. So the whole thing cancels out, which is why the integral over the whole sphere is going to be 0. As a result of that, then, well, assuming the various functions are in C1, and well, or something. But anyway, and then as a result, the divergence theorem, which equals to this thing, it would mean, let's see, where is it? Yeah. Anyway, so the divergence equals to this, and as a result, that means divergence of the curl is equal to 0 for any for any v, for any sphere. So by the mean value theorem, then the divergence of curl is equal to 0. So that's problem 15. So problem 16 is about the integral is curl grad f is identically 0. All right, and so I have some of the stuff written here, and if we have this deal, then and if y is grad f, then we have the various requirements where Q3 equals to and R2, etc. So then the integral is equal to 0 for every closed gamma. Okay, that means that the double integral of theta dot curl grad f is going to be 0 for every sigma that's bounded by every closed gamma, basically. So then we can use the MVT to say that, well, in that case, if we let theta to be one of the what are those things? Unit vectors or something, then that will show each component of curl grad f is going to be equal to 0. So that and therefore it is 0. So that is that's about it for problem 16. So next, let's look at problem 17. All right, problem 17 on the following page, we have a problem that's similar to basic calculus, where we have an interesting condition. If p dx and q dy and r dc can be multiplied by some lambda function, and if they made in that case we'll make them an exact differential, then this following long situation is a long equation is going to be 0. Okay, okay, so let's do that. I have let's see. So we have PQR multiplied by lambda is going to be exact. All right, so then that means there exists some kind of a potential function big F, such F1 is P lambda, etc. And then and the Stokes theorem's requirements are satisfied. That is Q lambda 3 is equal to R lambda 2, which after etc. So after we do the differentiation, we get 3 equations. Okay, and so Q lambda 3 plus Q3 lambda plus Q lambda 3. That is, I'm doing the partial differentiation on both sides, so I get 3 equations. And then the next trick, and here's at first I didn't know what to do after this, and then eventually I tried something, but that didn't work. So then eventually I realized there's actually a very simple thing we can do. We'll rewrite this equation as this. That is, we'll sum up lambda on one side and put the lambda 2 and lambda 3 on the other side, okay, for the first equation. The same for the others. Lambdas are on one side. And then once you do that, then we'll take p multiplied by the first one on the left. We'll multiply p on the left and the right side of the first equation, q on the second, and r on the third. And then when we round them all up, then this thing, which is what we're looking for, equals to this, which checks out, okay? If you notice the color codes things all subtract each other out, and this does equal to 0 when all is done. And as a result, then this thing equal to 0 as is required. So that is problem 17. And you can, I also double check this equation to be indeed 0 on problem 13 here and 14 here. Okay, just some quick doing some quick partial differentiation there. And so that is that. And then next we have problem 18, which is over here. All right, and problem 18, we have to do things the old way, I guess. What are we doing? Compute directly, okay, and by using Stokes theorem, but calculate Stokes theorem the old-fashioned way. Okay, that is what I did right here. We have, first we compute directly, plugging in stuff, and that equals to something, okay? I calculated that to be equal to pi. And then by Stokes theorem, we have the line integral got converted into the surface integral, which we'll directly calculate. By doing the grunt work, okay? Where being that sigma is the hemisphere, cosine gamma equal to z, that was done on page 234. that I copied there. The same thing. And then continuing, then we just calculate things by doing the, what is that? Well, whatever that is, I just plugged it all in. Where this part is x, and that part is z, and then and that's d, I guess. But anyway, so all this eventually come out to equal to pi, just like the original calculation. So that must be correct, and that marks the end of this section.